So, good evening all. So this will be our final session. I mean, we will have an extra session, but according to this coursework, and this will be our final session, the session 12. So basically we have studied different types of phase transformations. So this course is based on phase transformation materials. So we have seen first what is phase. So and we have even discussed a little bit of thermodynamics, and also we followed by that we discussed nucleation, how the nucleation happens, right? So for a phase to form, there needs to be a nucleation part, right? So for nucleation to happen, there are certain cases, right? So there are thermodynamic cases, and also there are kinetics part. So apart from like thermodynamics, we also discussed kinetics part, right? It's not just we not only discuss thermodynamics part, we also discuss some kinetics part, right? Now, moving on to this session 12, which is our final session. In previous class, we have discussed the spinodal decomposition, and also bits and pieces about pinodal decomposition. So the basic difference between the spinodal and so the basic difference between the spinodal and the pinodal decomposition, right? We want to know. So I have discussed briefly, but again I will discuss that again. So now there are two parts. One is spinodal decomposition, and binodal decomposition. And this spinodal decomposition has again two parts, right? So one is our chemical spinodal decomposition, and coherent spinodal decomposition. Right, so these are the two parts I have discussed. Now, as I have discussed before, the difference between the spinodal, now the difference between the spinodal and the binodal, right? So these are the two types of decompositions, and these are one set of phase transformations, right? So there are different types of phase transformations. We have seen eutectic, eutectoid, pertectoid, monotectic phase transformations. So among those phase transformations, one is these are the diffusional transformations. And in diffusionless transformation, we have metastatic phase transformation. Right. So for diffusional type of phase transformation, we have one the spinodal decomposition and the other which is the binodal decomposition. So these two are the two topics we have discussed before. So let me again mention the difference, the main difference between the spinodal and binodal decomposition. Now coming to the spinodal decomposition, we know right how this diagram came. At this the hump, or we can call it like this hump in phase diagram, and in G versus X composition diagram. So this is G minus X composition diagram. So it will look like this, and this is a non-conventional, right? But in conventional cases, we have seen, or you more easily can be called as ideal solutions. In ideal solutions, we have seen that this will look like this. I inverted parabola, right? It looks like a parabola. But I cannot say the hyperbola because hyperbola has two foci, right? Again, I will explain this just for clarification only. So, if this is my parabola, so for example, this is my parabola, and I have only one foci, right? If I'm talking about hyperbola, hyperbola has two foci, right? So that's why the G versus X convolution diagrams are called as parabola rather than the hyperbola. Now, coming back to our discussion, so how this hump came from? Like this extra hump. Actually, it should look like this, right? So where that hump came from? That came from the delta H term. So delta H term has this omega term times XA and XB. If you write it normally, then it will become XA square XB plus XB square XA. And this can be written as like this also. All I'm doing is just I'm multiplying XA XB with XA plus XB. Then this will turn out to be XA square XB plus XA square XA, which can be taken out as a XA and XB common when we are writing the chemical potential terms. So I have wrote this thing previously. If you do not know, please go back and watch those previous videos. Now, coming back to here, this omega terms contain the bond energy term, right? So the bond energy of AB is half of bond energy of AA plus bond energy of BB. Now which one is favorable? Now that is the importance. If this is more negative, then this will be a negative term, right? So A prefers B. This will be more negative. Now if this is negative, or this is more negative and this is less negative, then this term will become positive. Why? Because there is already negative here. The negative will be plus, so it has higher value when compared to this value. That means it will become positive. So what will happen? I have delta G as delta H minus T delta S. Now what is my delta H? Delta H will be gamma XA XB minus T, and we know RT XA ln XA plus XB ln XB. Right. Now if this term becomes negative, then this will come down. If this term becomes positive, right, so at the extremities it is negative, it is still negative because this term is more dominant at the extremities, right? Because this term will become 0 if one of the terms becomes 0, right? So this term will be not even considered because it will become 0 when you make XA equals to 0, tends to 0, whereas this will not become 0, right? So yeah, slide. Now here it is. Now XA XB are becoming positive. It means if this term become positive, then at extremities let's write dou G by dou X. Let's do a differentiation, right? A simple differentiation. What will happen? So if I am trying to do with respect to XA, then it will become XB times, and we know XB equals to XA, 1 minus XA, so it will become, so 1 minus XA, if I differentiate it, if I do this term, then I will remain with minus XA, right? Because I already have X-ray and I have a minus term, so I'll remain with this. Now minus RT, right? So it will become XA 1 by XA plus RT ln XA. So omega XB minus XA RT 1 plus ln XA. And the same goes for the other one, right? So it will become RT 1 plus ln XB. So for simplicity, let's do it, because I'm not sure whether the plus or minus term will come here. So let's do it, the whole differentiation. Right, I will do simplification here because you may not understand this one. So if I do XA 1 minus XA, so if I do first differentiation with this one, then I will remain with 1 minus XA, or which is XB, I have written here, plus if I differentiate this one, it will become minus 1, because it will become 0, it will become minus 1, so it will become minus XA. So XB minus XA. This is what I have written here. XB minus XA, this one. Now, coming back to 1 minus XA ln 1 minus XA. For differentiation here, this will become minus ln XB. The next one is plus 1 minus XA, right? So if I do differentiation, it will become 1 minus XA. So 1 minus XA will be here, it will become 1 by 1 minus XA, and again I have to differentiate from this one, this will become minus 1. So this will get cancelled, so minus will come out, minus RT 1 plus RT 1 plus ln XB. I can directly write XB, right? 1 minus XA plus. So if I do the minus term, multiply XB minus XA minus RT 1 plus ln XA, or I can just cancel out this RT term, they will get away. Now I will remain with RT ln XB minus ln XA, and we know ln A minus ln B will be ln A by B. So omega XB minus XA minus RT ln XB by XA. Right, and for simplicity you can just put it with this one. Now if I come near to if I go near to XA tends to 0, right? Dou G by dou XA, or XA tending to 0. Now if I substitute 0, it will become 1 and it will become 0. So again, ln 0 is not defined, or it will become minus infinite, right? And because of this minus term, it will become minus infinite. That's all. So this will become minus infinite. So that means the slope will become like this. That means it is 90 degrees. So G value will shoot up. That means we need so much amount of energy to get a pure element, or a pure metal or material. So that is the case. Now, and we know at the extremities it is tending to, it has this slope. So at extremities it has this slope. Now what about at middle? At middle, this term will dominate, right? So if this term dominates, then that means the delta G value become positive, right? So it becomes positive at one point. The delta G value increases, so that means at middle you have maximum value. So if I just extrapolate, and it will look like this. Draw it again. Okay. Look like this. Now there are some points. There are 2 points. Right. So what is happening here? If this is my slope, so my slope is changing. At here my slope is 90. So at here my slope is 0. That means what is happening? My slope is decreasing. Again from 0, my slope is again changing. Again my slope is 0 here. Right. That means in between. See, I have slope 0 and 0 and 0 here. So I have 3 cases. I have slope as 0. That means there are 2 cases. If the slope is 0 between 2 points, so if I have one point and if I have another point and my slope is 0, so slope S1, slope S2. So if my slope S1 and S2 are 0, then that means, what do you mean by that? So if my slope S1 and S2 are 0, then that means there are 2 cases. This first case and the second case. These are two basic cases, right? We can even put so many different type of mathematical, more complex mathematical cases, but for simplicity we are only taking 2 simple cases. The first case is if 2 points of 0 slopes, that means in between these 2 points it is a straight line. So it is a straight line connecting to one point and another point, right? So that is a case. Now what about the second one? In the second one, the slope from 0 might increase to some certain point and then again decrease to that value. It's more like a sinusoidal delta, right? So in sine wave, at first you will have 0, then you will reach 1, and again you will have 0. So that means what is happening? The sine function is constantly increasing to 1 and then again decreasing to 0, right? So if it is 0, 1, 0, constantly increasing to 1 and then it is decreasing to 0. So again it will go to a negative value, minus 1, and again it will come to 0, and again it will go to 1. So that is what's going to happen. So the same thing if you follow here, then that means, so the slope is increasing, right? So that means the dou square G by dou x square is positive here, from here to here. I will write it again. So let me almost write so for more understandability. So this is my G versus x, right? This is curve, this is my hump. So I have slope, this is 1, 2, 3, and there is one nodal point 4, another nodal point 5. So from 1 to 4, slope is increasing. Right. That means the dou square G upon dou x square is positive. So you cannot greater than 0. Is positive. That means greater than 0. Positive, i.e. greater than 0. Now from point 4 to 2, now this is some a peculiar case. not in terms of mathematics, because you can have dou square is equal to x square equals to negative. That means that is a convex, right? It's like negative. It is peculiar in material science. Slope is decreasing. So that means dou square g upon dou x square is negative, i.e. less than 0. Right? So you can understand, right? So people can understand. So dou square g by dou x square is positive. That means greater than 0 here and less than 0. Now, coming to, if my composition lies here, what will happen? And when my composition lies here, then what will happen? So there are two cases. This is for case 1, this is for case 2. Let's write it for case 1. Wait. Now okay, for case 1, dou square g upon dou x square is positive. Then that means if I am at composition 4, if there is a slight change in free energy, for example, if I move, so if this is, let's say, if this is my point here, this is how it looks like, right? This is my 4. If this is my below, it should be below. Below composition 0.4, right? So here you have 4 and I am below 4, right? So then what happens? That means if my composition is changed, right? Composition is changed, then my free energy increases. What does that mean? So for that thing to happen, so for if there is an increase in composition energy, right? So if I am changing the composition, slight change in composition, my free energy will increase. So what does that mean? It means so if my composition is changed and the free energy is increased, so the meaning is there is that state is a metastable one. That means we need to apply certain amount of energy. We need to apply some energy. That means it is not a total equilibrium state. And how do we achieve that state? By doing nucleation. Nucleation and growth. So this case is also known as the binodal decomposition. Binodal decomposition. Now this is the case for binodal decomposition. Now what about the spinodal decomposition? Now what about the case? Case 2. The spinodal decomposition. And now here, this also known as spinodal decomposition. Now what is happening here? Here, right, dou square g upon dou x square is negative. That means less than 0. And also change in composition will result in decrease in free energy. right? So that means there is no need for nucleation. That is what it means. So change in composition will result in decrease in free energy. So there is no need for nucleation. That means it is spontaneously decompose, dissociate. Right, so that is what we call as spinodal decomposition. Now the basic difference between spinodal and binodal decomposition is there is no need for the nucleation in spinodal, but in binodal we need the nucleation. Right, so that is the difference between spinodal and binodal decomposition. Now we are cleared based upon mathematics. Now coming to how actually they form, right? How actually the spinodal decomposition happens. Right. Now here you can see at first I have, let's say the two phases, a single phase is dissociated into two phases. Instead of writing like this, I can write like this, right? It will be more good. Alpha will turn into alpha dash and alpha double dash. These two are different phases with different composition. Right, you have different composition. Now let's say my alpha dash is at here, my alpha double dash is at here, my alpha is here. Initially this is my composition, alpha composition. Now if there is a small change, or there is a compositional disturbance at some point, so what's happening is there is a compositional difference. That means the alpha, this is my alpha. Now this disturbance will grow. Right, so I will show this in regions. So if this is my microstructure, up to here I have right. Okay. So let's say I have 4 regions here. At first, because of this disturbance, this region starts to lose atoms, starts to lose solid atoms. Right. If this is my alpha composition, then I will start losing B atoms. So my composition decreased. Now the next thing is, here, because of the solute decrease, whatever the solute atoms were there were rejected outside. Where they are rejected? Onto the surface, right? So away from the point. So they gets accumulated here. And here my composition will increase. Now again, and because this region is rich in A, then the region besides, or the region left and right to this one, they will get depleted. Right? So they have a less composition. Again, the same thing will happen here. Right? are more rich in. If I try to join, so this is what we see here. Right now, if I try to increase my composition, so if I am trying, and this curve will keep on growing. Right? Why? Why? Because there is a concentration gradient, delta C, and from which you can take it as chemical potential. So diffusion will happen for initial cases. For simplicity, we can say the diffusion happens because of the concentration rate minus T rho C upon rho X for downhill diffusion for simple cases, but the diffusion happens because of the chemical potential, and this is explained for both uphill and downhill. Right? Now, and this will grow with time. So finally, they will reach a composition where here you can see in this case. So we will attain certain composition like here, alpha 1 and alpha 2. So this is what it means. So if I am here, then my composition will decompose into this one and this one. Right? That's all. If I am here, then it will try to decompose into this one and this one. That's all. Therefore, we have seen what are the governing equations for any nucleation. Right? So, what are the governing equations? First one, when we are talking about the nucleation, let's add slide. Equations governing for nucleation. And first, I have delta G. So delta G nucleation I have the volumetric term delta GV, which tells me what is the amount of transformation that has taken place, right? So this term is negative term because this is the term that's going to make free energy decrease, right? This is the term governing for any reaction, for nucleation reaction to happen or not. This is my delta GV term, volumetric free energy, and I have surface energy term, and also I have strain energy term. If I try to combine delta GV minus delta CS plus A, for example, if I am talking about solid liquid, not solid liquid, rated for alpha 1, right? Gamma alpha. Now this is the total part of nucleation. For any nucleation to happen, and for example, if we are talking about sphere, right? So if sphere gets transformed of radius r, its form of radius r, it has volume of 4 by 3 pi r cube delta GV minus delta GS plus 4 pi r square. So if I do dou delta G by dou r, then what will happen? It will become 4 pi r square square delta GV minus delta GS 8 by R. So for critical state this might take as 0, right? And this will turn out to be, I can take R as a common, 2, so I went into pi and remind with R delta GV minus delta GS plus, this is for minus R, plus 2 gamma alpha dash. Right. So I have two cases. One, R equals to 0, that is for initial case. This is for initial case. And the next case is R equals to 2 gamma alpha dash upon delta G minus delta GS. This is for sphere. And for this one, and for spheroidal decomposition, this can be taken directly as delta GC will be half dou square G upon dou x square times delta x. So that will give me the delta GC. So more is the compositional difference between them, the higher will be my volumetric free energy. Right. Now that is for my volumetric free energy. Now what this is my the areal free energy or surface energy, or the surface term which is dominating. Right. Now higher is my compositional difference, the higher will be my surface energy term. Right. Now if my strain energy term is higher, that also will depend, the higher will be my compositional difference now on how this comes. Now for example, if I have two same type of crystal structures, right, what do I mean? So for example, right, now what do I mean by that? So for example, if I have an isomorphous phase diagram, right, now for an isomorphous phase diagram, so for example this has a lattice parameter of 4.01, it's quite large, so let's take suppose if I have 2.04 angstroms, 0.14 angstroms. Now this guy has lattice parameter of 2.08 angstroms. So that is how when I am trying to infuse my B atoms into A atoms, there will be straining in the lattice. Right, so the lattice will have different lattice parameter. So this is how the lattice parameter will keep on increase, and if I reach the pure B, I will have 2.08 angstroms. So that is what it is. Now, if I have a compositional difference, then I have grains of different lattice parameter. Right, if I have two phases, this is my alpha dash, which is this parameter, and alpha double dash, which has this lattice parameter. And now if they have two different lattice parameters, and what I'm trying to do, I'm trying to accommodate, right? I'm trying to form a grain boundary. So if they form a coherent precipitate, coherent or semi-coherent, there needs to be straining of lattice planes, right? Why? Because they have two different lattice parameters, and for them to have minimum grain, minimum free energy, minimum surface free energy, surface energy, they need to form the bonds of the grain boundary, and need to form the bonds. Then because of the different lattice parameters, they need to get strained. The atomic planes need to be strained, and for the atomic planes need to be strained, we need to do there need to be accommodation here, right? Now that's what I'm saying. That's what I'm trying to imply. If there is a large compositional difference, just like here the delta x, that means there is a large difference in lattice parameter, and we have large difference in lattice parameter. There needs to more straining between the grain boundary, right? With the boundary, there needs to more straining for that to accommodate, and that will increase our, what do you call, the strain energy. So if delta x increases, the volumetric free energy will increase. If delta x increases, the surface free energy will also increase. If delta x increases, my strain free energy also will increase. So there needs to be a point where this term will take care of these two terms, right? So this is my delta Gv, delta G area, delta G strain. This is surface. This is my surface energy. This is my volumetric energy. This is my surface energy, and this is my strain energy. Right, so these are my 3 points. Now, so these are the terms. See, this is my volumetric energy, this is my surface energy, this is my strain energy. Volumetric, surface, strain. If this becomes 0, that means everything is balanced, or for our spinodal decomposition to happen, so I have the 3 terms here. So one is my the volumetric surface energy, the aerial surface energy, and strain energy. Now what happens if my aerial surface energy is not there? So that means I do not have any aerial surface energy. There is no new surface that has been formed. So that is what it means. So what do I mean by there is no new surface that has been formed? That means this will turn to be 0. If I have no new surface that has been formed, if I have no new surface that has been formed, that means I have a coherency, right? And I have coherency, but then might have straining because of the different lattice parameter, right? That might be possible. So that's why I have this term, the strain term. I still have strain energy term, but I do not have the surface energy term. That means there is no new surface that has been formed, but still, even though there is a formation of this grain boundary region, there is a matching, but still, if because of the different lattice parameter, there won't be a perfect matching. I mean, there is matching, but to have that perfect matching, the atomic planes needs to be strained. Right, so for example, if this is atomic planes, they need to be strained, right, to accommodate that perfect matching. So that is and now this phenomenon is called as coherency spinodal decomposition. Right. Now, moving on to how the spinodal decomposition looks like, the micrograph. Spinodal decomposition. Micrograph. Okay, so how do we get this image? We get it image from BSc image. Now how the BSc imaging happens? The BSc and in SCM, the backscatter electrons are scattered in a way such that, so if this is my sample, let's say this is my electron beam, right? Electron beam, then the electrons, if this is my interaction volume, from this you will have the BSc, the backscattered electrons. So the backscattered electrons are more prone to deflection or more scattered with respect to the atomic number. The higher the atomic number, the higher will be the backscattering. Right, so keep that in mind. So higher my scattering, the higher the atomic number, higher is my scattering. That is what it means. The higher atomic number, the higher scattering differences mean. Right, now going to the next one. Now next type of phase transformation is my cellular phase transformation, cellular precipitation. Now before going to that, let's talk about what is precipitation. Right? Let's talk about precipitation. Precipitation is achieved when my initial solution reaches a supersaturation solution. Now again, what is supersaturation solution? Supersaturation is nothing but reaching a point where the solute concentration is beyond the saturation limit. Right. So, in simpler terms, supersaturation happens when we reach, for example, at high temperatures. For example, if I'm high temperature, right? So if I'm at, for example, if I take an alcohol A and B, and if I'm at high temperature, for example, if I'm at 1200 degrees centigrade, the solubility of B in A is, for example, 4 weight percent. Right, if I'm at composition of 4 weight percent, at 1200 degrees centigrade, the B is completely soluble in A. Now, if I decrease my temperature from 1200 degrees centigrade to room temperature, then what happens? If I try to decrease my room temperature, then my solubility limit will drop. So let's say my solubility limit will drop to 1.28% of E. So now if I cool it slowly from 200 degrees centigrade to room temperature, then it will slowly, how should I say, if I do the equilibrium cooling, then this phase, whatever the phase, it will reach to 1.28%. But so at first I have, for example, I have alpha phase, and this alpha phase will dissociate into beta and gamma phase. Now beta has 1.28% of B, and gamma will be rich. Like for for example, if I have the gamma will be like which of 7-weight% of, or if we even say, if I am talking about retrograde phase diagrams, so that there is a need of a diffusion, right? So it will take longer time to have larger compositional difference. So that's why. So if you can see, for example, if I'm just telling based on assumptions, so one example type of phase transformation, eutectic phase transformation. Now, eutectic phase transformation contains liquid turning into two solids, alpha plus beta. Alpha might have, so for example, if I'm liquid and liquid has the composition like if I'm at 8-weight% of B, and if I try to cool it, I do the solidification, then alpha might have 2-weight% of B, and beta might have 90-weight% of B. So this much amount of compositional difference is only allowed when we are traveling from liquid, because liquid has good diffusivity of solid atoms. I shouldn't say good, it has a great diffusivity of solid atoms when compared to solid phase. Right? In liquid, DL diffusivity, of B in liquid is very much greater than diffusivity of B solid. Right, and to accommodate this much difference in composition can be only achieved when we are trying to come from liquid to solid. Right. So if we talk about the eutectoid solidification, right? If I am talking about eutectoid solidification, the eutectoid solidification, one type of phase will convert into two different types of phase. Both are solids. Everything is solid. This one, this two, this three. So there is involvement of three solids. Right. When we are seeing this eutectoid type of solidification, now what is happening here? So let's take the famous example of steel. Eutectoid. Gamma and 0.88%. Alpha 0.88%. Of 6.67%. Carbon. Now, the compositional difference is small, right? Here, 6.67 and 0.2%. This is the compositional difference. But here, in eutectic phase, the compositional difference is how much? 88. Right? So, but here it is not that much. So, in eutectoid transformations, there is a limit for diffusivity. because system needs a large amount of time to achieve the equilibrium state. Right, so that means the metastable state will go on happening. Right, so the G value will go on decreasing for large periods of time. It doesn't happen in for a few days or months, it can even take few years for the total diffusivity to happen, for that much compositional difference. Right, so that is the difference you can see. For eutectic and eutectoid, the compositional difference is not very large when compared to eutectic and eutectoid transformations between two phases that has been found. And why it only refers to the diffusivity of atoms. Right, so that is one thing. Now, again coming back to what is precipitation. Precipitation is nothing but formation of a new phase because of formation of two different phases from parent phase why? Formation of two different phases from parent phase because to decrease the total free energy. And to avoid supersaturation. Supersaturation is not a stable state. Right, so my supersaturation is metastable state. Now I want to achieve a lower state, right, the equilibrium state. That is what it means. I want to come from metastable state to equilibrium state. Just give me a second. Now, this is about precipitation. Right. So for precipitation to happen, first I need to go to a more saturation state. Then when I decrease the temperature, I have to choose a certain composition where at high temperature the solute solubility is high, but at low temperature the solute solubility is low. That way I can form supersaturation while cooling. But sudden cooling, if I do the thermal cooling, the normal cooling or slow cooling or equilibrium cooling, then I have the formation of phases, two different phases. Right, so that's what we do in edge hardening, precipitation hardening. Right, so we have seen now that is about the precipitation, the precipitation. I shouldn't say not. Let's not talk about the precipitation hardening because let's not talk about the precipitation hardening because we have seen this type of phase transformation in previous sessions. So yeah, people can easily refer back because it is like 2 or 3 sessions before, I guess. Yeah. So moving on to the cellular precipitation. Now where do this precipitation happen? This precipitation happen at grain boundaries. Now again, why? The grain boundaries do not follow asymmetry, right? So the atoms are more randomly distributed there across the grain boundary. And also to minimize this surface energy, and because there is a grain boundary, then that means there is an interface. If I have an interface, then accordingly you have surface energy or interface energy. Now to minimize that interface energy, a new phase will form. That means the final free energy we are trying to decrease. So now to minimize this surface energy, a a new phase will form on that, right? And now so the precipitation, the grain, now the grain boundary precipitation, even though this grain boundary precipitation need not to always result in grain boundary allotropes or Widmanstatin side plates, right, or needles formation. Now, in some cases, it can form a different type of transformation, and that is known as, and that's what we're going to discuss, and that is known as a cellular precipitation. In one case where a different type of transformation that can result from grain boundary precipitation is cellular transformation. Now, here the grain boundary moves with growing tips of the precipitates. Now, before some phase forms, so for example, in if I take now the basic difference, how the basic difference can be explained, the difference between the cellular precipitation and normal precipitation. So in eutectide transformation, so I have a gamma phase, gamma 1 and gamma 2. Now if I try to decrease my temperature, so what happens? So for example, if my alpha forms, and besides that there is a formation of Fe3C, right? So this is my Fe3C, right? So this is my alpha, this is my Fe3C, right? These two are Fe3C and that is my alpha. Now there is completely new type of thing has been formed, new type of phases has been formed. Now there is no grain boundary here. Why? Because at the grain boundary there is a new type of phase has been formed. Now one can see this is not moving, it is still stuck here, right? So this is my new phase, and this will grow, right? And the grain boundary will not grow. Now what happens in the cellular precipitation? You can see here, at first I have, let's say, alpha dash and alpha dash. Now a new phase will form. Let's say it is my alpha, right? Now if my alpha wants to form, once the alpha form, it will try to grow, right? So this will try to grow. Let's take a different color, and this will try to grow. This is conventional, because once a nuclei forms, it will try to grow. Let's say this guy is richer in B, so this color is richer in B, right? So precipitation will happen. Let's say a binary aula, and my precipitate is very highly rich in B. So this my precipitate is rich in B. That means the surrounding area must be lean in B atoms. So for example, it forms. Now you can see my grain boundary itself is being shifted. Right? So that is what happening here. this will grow. So that is what we have. A new type of precipitate is being formed here, and if it tries to grow, then the composition here get leaned. So it also needs to grow so that it can accommodate. So for example, if B grow, so this is my B, and it has grown, right? It has formed a cellular structure, right? Now for this to grow, there is a need, there is a supply of B atoms, right? So there is a need for supply of B atoms. If my grain boundary stays here, so if my grain boundary just stays here, then how the atoms are going to supply? Right, the atoms cannot jump from here to here, that is very long distances. So this will also grow with this guy. So this is what we see here. So this grain boundary will also grow so that it can supply the atoms to B, to this precipitate phase, and they will just grow like this. So the whole grain boundary has been moved. So that is the new type of phase transformation. That is called a cellular transformation. Now again, I will explain it again. The essential feature of this type of transformation is that the boundary itself moves. Right, the boundary itself moves to accommodate that B atoms to for the precipitate to grow. Right, and again it is very similar to detector transformation. Why? Because at first I have alpha phase, alpha dash phase, it will become alpha plus beta. But the only difference between here is the alpha dash and alpha both are similar. Right, the only difference is the alpha dash and alpha both are similar crystal structures. For example, if it is my FCC, this will also will be my FCC, and this will some other structure HCP, for example. Right. So the only difference is the compositional difference. This has, for example, 2.4 weight%, and this will have 2.1 weight%. For example, if I take 2.1 weight%, it's just for example purposes. That's all. So that is the main difference. It will lean in B. That's all. Now, here the grain boundary nucleation develops into cellular precipitation, right? Differs from it can be different from one alloy to another, and still it is not fully understood. And the reason why some grows and some doesn't is also very unclear in cellular precipitation. There are still the further studies needs to be studied. Now, there are different examples, right? So this is my magnesium alloy. Magnesium, it is alloyed with aluminum. Magnesium aluminum alloys. So one can see the beta phase in this case is a precipitate. So let's say my precipitate is magnesium 17 Al12. So this is my precipitate. Right. Now how do this phase diagram look like? So I have discussed before, for this type to form there is a need for supersaturation state. Now how does the supersaturation state will come? If the solubility of aluminum atoms should be high at certain temperature. Right. Now, let's say this is my beta, this is 0.4. Now this is my alpha, this is my magnesium. We will go aluminum here, this is my 8%. There is this. Right. Now, and suppose I am at this composition. let's say I'm at 0.18%. Right. So at, what should I say, above 400 degrees centigrade. So let's say this is my 400 degrees centigrade. Now if I'm above 400 degrees centigrade, I can say that my whole composition is a single phase homogeneous composition of magnesium aluminum alpha phase. Magnesium aluminum alpha phase. Right. Now if I try to decrease my temperature, then my precipitate will try to form. Right. If I'm at this temperature, using Thailand rule, I have derived how the Thailand rule is even derived. So, or liver rule, how that is derived. So from that we can say this will, what is my phase fraction? Right, I can easily let's say this is my 0.4, right? And let's say this is my x1, and a fraction of x2. So the fraction of alpha will be given by x2 minus 0.1 upon x2 minus x1. What will be the fraction of beta? Beta will be given by 0.1 minus x1 divided by x2 minus x1. So this will tell me what is the phase fractions. Right. So this will tell me about phase fractions. Now, moving on to this. Here you can see there is a laminar structure, right? So these dark lines shows the precipitates that has formed. So more or less a laminar structure, right? Here you have precipitate and in between you have alpha phase. Now the grain boundary between the grains 1 and grain 2. So this is my grain 1. Let me write it in red color. So this is, yeah. So this is my grain 1. This is my grain 2. So these are my two grains. Right. Now the grain boundary between grain 1 and grain 2, so before this reaction it should be a straight line. So it was a straight line before the reaction. Right. But what happened now? It has been displaced. So before it was a straight line. Now after the reaction it has been displaced. Right, so this is my grain bond after displacement. Right. Now the growth of this cellular precipitates requires it requires the partitioning of the solute, right, to where? To the tips of the precipitate. Now this is my phase diagram, right? So again I have explained this. For a precipitate to grow, the atoms must transfer from here to here. Right, so that's what we have seen in cellular phase. That's what we have seen in reductide phase transformation, in perlite phase transformation. Right, we even derived how this growth will depend upon the compositional difference. right? So this is my alpha phase and this is my Fe3C. So the compositional difference will define what is the growth rate of these precipitates. And also, it also depends upon undercooling. But it also depends on undercooling. But one point is that it depends upon the concentration difference, right? So that is one point to remember. For atoms to transfer, the atoms must be transferred from one phase to this phase, to the tips of the precipitate. So if this is my precipitate, the atoms will be transferred from the alpha phase to the precipitate. Now, how can this be occurred? This can be occurred in two ways. The one is through diffusion. Now how? The diffusion through the lattice ahead of the advancing cell front. So the first case is the diffusion. How this will happen? Through the lattice ahead of the advancing cell front. That is one case. Now what about the second case? It can also happen by diffusion in the moving boundary. The next case is diffusion in moving boundary. This might be a little bit complex, so that's why the studies are still going on these type of phase transformations to understand how they are happening. Right. So the diffusion happens in two cases. One, diffusion through the lattice head of the advancing cell front, or see. So the diffusion to this is my advancing cell front, right? So this is my alpha. This is my precipitate. This is my alpha precipitate. Alpha precipitate. So diffusion happens through the lattice ahead of the advancing cell front. So this is how the diffusion will happen. Now, this is one case. Now, what is the second case? The second case happens the diffusion in the moving boundary. Right. So diffusion in the moving boundary. Here, and these are the two types that will happen. Now again, the partitioning by the lattice diffusion, right? There are two types of diffusion. I have said. So there is one, there is two. So keeping in mind these two types of diffusion mechanism, we can relate how the growth can happen. Right. So to understand this, let's see. The partitioning by, like first case, the lattice diffusion would require absolute concentration gradients. Right. So that's what we need, a concentration gradient for that to happen ahead of the cell front. Right. So ahead of the cell front, there is a need for concentration difference. So if I draw, this is my cell front. So there is a need for the concentration difference. So from point 1 to point 2, this is x1, this is x2. For atoms to diffuse from point 1 to point 2, we need 1 to 2. For diffusion flux to happen, there is a need for concentration gradient between these 2 points. That is one. If the grain boundary ahead of cell, while if the grain boundary is most effective diffusion route, right? So the grain boundary can act as a most effective diffusion route. Why? Because at the grain boundary, the atoms can freely move when compared to in the cell, because at the grain boundary, the atomic bonds, some of the atomic bonds are not satisfied. Some atomic bonds are not satisfied. But whereas in the grain, I have full coordination. Full coordination of atoms or atomic bonds. That is what is seen here. At one point you don't have a coordination, at another point you have full coordination of atoms. Right? Yeah. And that's why, so for the diffusion across the cellular region to happen, the diffusion across the cellular region to happen, there is a need for concentration gradient, and that concentration gradient can be provided when new precipitate forms, because of when new precipitate will have a higher concentration when compared to the previous one. Right, so right, so that is the case for this one. If we are talking about the diffusion across cellular. So these are this is the case for the diffusion along the boundary. Right. So the growth of cellular precipitates requires again the partitioning of the solute. Right. Now, in case of magnesium aluminum alloy, it has been in case of the magnesium alloy, so in case of magnesium aluminum alloy, it has been possible to do the microanalysis, right, with different types of high resolution, spatial resolution technique. Now, the results of this measurement, the magnesium alloy measurement, here the magnesium alloy one, it clearly indicates that the advancing the matrix composition remains unchanged to within 10 nanometers of the advancing cell, right, so that the partitioning must be taking place within the boundary itself, right. So that means the composition is not changing. So here it can be seen here. Slide, yeah, here it can be seen. The atomic aluminum diffusion. So this is the aluminum percentage with respect to the distance. And this is my grain boundary. Right, so that is the differences. So that is the difference. Now for magnesium alloy, uh, you can see here. So if I show it here, and for magnesium alloy, there is a diffusion along boundary, so that's resulting in the same composition up to 10 nanometers, right? So this is the difference between grain boundary alpha and alpha dash. This is about the cellular transformation. Now, there are other names for cellular precipitation. The cellular precipitation is also can be called as the discontinuous precipitation. Discontinuous precipitation. Because you can see the composition of the matrix changes discontinuously as the cell front passes. Right? That's what we see. At first I have an alpha dash matrix, and once this grain boundary starts to move because of the precipitate formation, right? So this is my cell, that's been growing, and because of this growth, the composition here will continuously change. Right, now that is why we call it as a discontinuous precipitation. Now, what about the precipitation which is not cellular? So the precipitation which is not cellular can generally be referred as a continuous, because it occurs generally throughout the matrix, or right, continuous because it occurs generally throughout the matrix on dislocations of grain boundaries, etc. And the matrix composition at any given point decreases continuously with time, right? And often general precipitation leads to finely distributed intermediate precipitate that is associated with the good mechanical properties, just like we have seen in GP zones and the precipitation hardening. These are the two types of precipitation type of reaction we have seen, right? Now the cellular reaction is then unwanted because the intermediate precipitates will dissolve as they are overgrown and replaced by the force equilibrium precipitate within the cells. Right, and because the uneven, discontinuous uneven growth of this precipitate, they are not preferable because of the Orban, because of astral ripening, where the bigger precipitates will just take out the smaller precipitates. Why? Because to minimize the surface energy term. Right, now this is about the cellular precipitation. Now again going back to the tetrad phase transformation, right? So phase transformation. Now in tetrad transformation we have seen, and for example an alpha phase. So let's take example of steel itself. 0.88% carbon steel, right? So it's not hyper or hyper, it's perfect 0.88% steel. So let me draw a phase diagram. Let's say I have here the Fe3C. This is an orthonomic crystal structure. Here I have gamma, alpha plus gamma, and in between I have alpha plus Fe3C, right? This is alpha plus Fe3C. Now this session. If I try to cool from gamma, let's say this is my gamma, and if I try to cool it, I will get alpha plus 7 times my orthoron structure. Now gamma is my FCC, alpha is my BCC, P3Cs, orthoron. So these are the different structures that has been. Now again, if this is my grain boundary, let's say this is my gamma 1, gamma 2. Right. Now again, we know the difference between two grains is nothing but same material, same type of grains or same material grains. The difference is the atomic plane orientation. If this is my orientation of 1 1 1 plane, then here I have an atomic plane orientation like this. So the difference is the orientation of atomic planes in gamma 1 and gamma 2. Now this is my grain boundary of gamma 1 and gamma 2, and if my precipitate starts to form, right? So if this is my precipitate that has been formed, so it's small so that I can draw a total cell, right? So let's say I form Fe3C first, right? So I formed Fe3C. That means, so my surroundings are being depleted in carbon atom, right? So this is my Fe3C. Let me write this Fe3C first. This is my Fe3C. Now my surroundings are depleted in carbon. So because of that, there is a formation of alpha. And same goes here. My surroundings have been depleted. Right. Now, again, because of that depletion, there will be again a different phase. This will go on continue. Let me draw one last one. So we will have a total colony, right? Yeah, this is my colony. Then I can write this colony as a 1, right? So we draw Fe3C here. Now it look good. This is my colony. You have pairs of alpha and Fe3C, right? And this will grow. How this will grow? It will grow because of the carbon atom diffusion. Right, now this is about retrograde phase transformation. Now the grain boundary will remain same. Now again, why they are forming on grain boundary? So let's do that. So we have seen in the heterogeneous phase transformation. So this is my surface, and before there was a surface, and now there is no surface there. Right? There is another type of surface that has been formed. Let's say this is M. This is, let's put it as G for understanding purposes. This is G. This is my gamma. This is my, let's say I formed a phase alpha here. I can say formation of alpha plus Fe3C. Right. Now because of this, and we even have derived for the heterogeneous nucleation how the radius or theta. This is my radius. Yeah. How this theta value and this surface tension, how they can be balanced. Right. For example, there was a famous equation. Right. After balancing, you get that. This is about this one. Now again, why they form, and because of this, the formation of a new surface you face on a grain. So this is, and because of these surface tension forces that's been acted, we had the delta G heterogeneous equals to delta G homogeneous times f of theta. Now what is my f of theta? F of theta is minus 2 minus t cos cube theta 4. This was my term. Right. Now again, what is my how this theta value can be varied? For just for example purposes. So for your example purposes. So what is the range of this f of theta value? We know cos theta value lies between 0 to 1, or you can even take minus 1 to 1 for extreme purposes. Let's take minus 1 to 1. Right. Now again, what about cos cube theta value? Cos cube theta value again will change from minus 1 to 1. Right, because it will not increase in between that. Right? Now, if I try to substitute, we're trying to do pure mathematical here. Okay? Now, what will happen? Let's take case 1. Theta cos theta as, what do we call, minus 1. Right. So 2 minus 3 cos theta is minus 1 plus, it will become minus 1. Right. If I substitute minus 1 there, then cos cube theta will again become minus 1. So 2 plus 3 minus 1, which is 5 minus 1 by 4, 4 by 4, which is 1. Now, that is case 1. What about case 2? If I substitute plus 1, then 2 minus 3 times 1 plus 1 cube. So 3 minus 3 by 4, it will be 0 by 4, it will be 0. So what does that mean? For theta equals to 0, cos theta will be 1. For theta equals to 180, cos theta will be minus 1. So theta value can range from -180 to 0. Right. What about f of theta? F of theta value should be right from 0 to 1. So we prefer f of theta will be close to 0. That means if f of theta is close to 0, then delta G heterogeneous will be minimum. Right, so delta G hetero goes to delta G homo times theta. If this f of theta values continuously decreases, it will continuously decrease because it is multiplying with some factor. Right, for example, if f of theta will become half, so delta G homogeneous, for example, my value is coming like 213, then it will become half of it, so which is more favorable to form. Right, so that is the amount of energy that requires for delta G heterogeneous to form, which is appreciable when f of theta gets value gets decreased. So that is about different types of nucleation. And after the in final few lectures, sir has discussed ceramics. Right, in ceramics he has discussed transformation toughening. See, I will not go deep into it because it itself takes so many lectures. So in ceramics, so how the deformation happens. So ceramics do not have very high toughness values when compared to the materials. Why? Because of the dislocation motion. So dislocation motion is not very much appreciated in ceramics when compared to the metals. Right. So when we go deep into the mechanical properties of materials, for dislocation you need a big Burgess vector. Right. And also it depends upon the atomic bond, which type of atomic bond you have formed. In terms of ionic bond, you have two atoms forming a strong bond, right? Which is not case for metallic bond. Metallic bonds are different when compared to covalent and these ionic bonds, right? And it has completely different bond values, bond energy values, right? So in ceramics, the major failure is because of the crack propagation. So sir has discussed the different types of mechanisms to control this crack propagation. Right. One is to divert the crack propagation. Divert. Crack propagation. Right. One can directly divert the crack propagation, or one can do this. So if I have a crack in a material, so if this is my material, if I have a crack growing like this, so what happens if I apply a compressive stress here? So application of compressive stress can lead to diminishing of crack propagation. So just like I have briefly discussed, and there will not be very much topics that are going to be asked in exams also. So this is about the transformation toughening. So that's all for this today's section, and we will meet in the last session, which is an extra session, which will be on April 16th. Yes, it is tomorrow. Yeah, it is tomorrow, right? So yeah, the April 16th. Yeah, it will be tomorrow. We will have an extra session for 2 hours. So kindly attend it. Who are going to write exams, because it will be very much helpful for them, because what we will try to just move on. We'll try to just see all the slides that we have been discussed here, and I will just briefly touch up the topics so that it can be good one-time revision for you. So not one-time revision, it can be just a revision for like 2 hours, where you can see every topic, the important topics, and the miscellaneous topics also, which some of you have mailed me related to few questions, few topics which needs to be like briefly touch up, so that people can understand things and easily can write in exams, right? So that's all for today's session. Thank you for attending all these sessions, and yeah, if you have any doubts, my mail is always there for you. You can mail me, and I will try to get back to you for those questions, right? So thank you.